This is Mr. Pillar for ECET273 Modern Energy, lecture number 13. We're going to talk about the electrical power systems. It's based on Unit 2 in the Pardo-Patrick text. So let's proceed. Here we have supply and demand. Much different use of supply and demand than other products, and electrical energy is a product. Power, production of power is production of a commodity, so it's just like making a hammer, just like making a car in a factory. The difference in our supply and demand is that we have no way of creating a surplus. We don't have useful large-scale storage devices. We're working on it. There are a few out on the grid. I spoke with a gentleman from the local power utility here, Indiana Michigan Power. He has indicated they do have on their larger systems for AEP, Indiana Michigan Power, the division of American Electric Power. They do have a battery essentially on the grid at least one site. They're not necessarily happy with its performance, and so we're working on better solutions. I've seen some articles on the MIT is working on some large-scale batteries. We're going to need that, particularly with alternate energies, but we'll talk about that later. The fact is, at the moment, we have no actual useful way of creating a surplus amount of power on the power grid. With that being said, we require accurate forecasting. What do I mean by that? We need to define what the load is going to be at any given time. But the fact of the matter is that that load varies over time. Over time of the year, there is a different amount of load that's demanded on the grid for summer, winter, fall, and spring. Over the week, there's a different amount and type of load that's demanded Monday, Tuesday, Wednesday, Thursday, Friday versus Saturday, Sunday. And then each day along the way, there's a different load demanded upon it on the day itself. Think about everybody waking up, everybody going to work, everybody working, everybody leaving work, everybody going back home. That load shifts constantly. Fact of the matter is that load is expected, that the people causing that load expect the power to be available in sufficient quantity whenever and wherever they want it. Particularly in the U.S., we don't notice when the electricity is there, but we certainly notice when the electricity is not there. To maintain that, we have a interconnection of our systems on a regional basis. Help support variable load demands. I can have a surplus of power on my generator. I am sitting here in South Bend, and for whatever reason, coal was cheap for me today, so I'm firing up and creating a lot of extra power, more power than my customers are going to need. I can take that surplus and sell it to a generator in Toledo because they needed to go down for maintenance. They need to maintain their customers, and they need to know that the load that their customers are going to demand is going to be maintained. And here in South Bend, I will maintain that. So that would be a regional basis of support of variable load demands. Alright, so what did I mean by regions? Well, here's the NERC regions, the North American Electric Reliability Corporation. Power companies are signed on with this conglomerate to help each other support those loads, as I described, between the power plant in South Bend and the power plant in Toledo. Each of these regions work together. Each of the regions are within a grid area. The grid itself, as we refer to it, is split up into three pieces. We have East, West, and Texas. East and West refer to east and west of the Mississippi. There's no actual real physical tie between those three grid areas, but this drawing here shows you the layouts of the regions. Alright, so we need, as we have supply and demand, we need a couple numbers to help us figure out where we're at. The load factor, or the demand factor, and the capacity factor help us figure that out. The load factor is the average load for a time period divided by the peak load for a time period. Capacity factor is average load for a time period over the output capacity of the power plant. So obviously the load factor helps identify what the load is. The capacity factor helps define what my power plant can do. Let's talk about that in a smaller scale circuit. Let's imagine we have a little robot. It has two motors, a sensor, and a microprocessor. At any given time, both motors could be on. The microprocessor could be running full processing capabilities, and that sensor could be really busy sensing. So we have maximum ampacity out of everything. That would be our peak load. Okay. Average load would be on our robot, probably the robot cruising, not turning on, just cruising, and nothing really to sense, and so there's no processor activity really going on. That would be our average load. So you can imagine that. Output capacity of the power plant in this scenario would be in the milliamp hours of the battery. In the power plant world, we'd be talking about the megawatts that the generator could produce. Alright, as I said, we're going to talk about power production. We're not going to talk about how we're getting the heat. We're going to talk about what we do with the heat to get the energy into electrical power. That being said, we're going to start with a steam turbine. I have a drawing here out of the Pardo text. This steam turbine is called a reaction turbine. We'll get to that. Power in the United States is mainly produced via steam turbines. 80% of the U.S. power comes off of a steam turbine. We're not talking about how we get the steam, we're just talking about how we get rotation on the generator. Basically what happens is we force steam into this turbine. The rotary motion spins the generator. We refer to that as the prime mover. The steam is the prime mover that turns the turbine. Okay? This, like I said, is a reaction turbine. Reaction turbine usually has more than one set of blades. Notice that it's conical in nature. The first set of blades reduce the pressure of the steam. By reducing the pressure of the steam, the volume goes up. Reach back and push off the cobwebs there from your chemistry courses and think about the ideal gas law. PV equals nRT. As you decrease pressure, volume must go up. So first it reduces pressure, increases the volume. So with that we have to increase the diameter, hence the conical shape. And increased diameter means we have to increase the diameter of the blades and the length of the blades. And the combined sections direct the high velocity steam to create rotation. They're all slightly offset to cause the turbulence in the steam to make the push happen. Also think back to when we talked about synchronous generators and synchronous motors. Synchronous motor speed is dependent on the frequency of the current that goes into the armature. In this case, a generator, it's the reverse. The speed of the rotation of the shaft determines the frequency of the current pulled off the armature, right? So we're very interested in the speed that the turbine rotates, and we need to maintain a constant speed. How do we maintain a constant speed? We maintain a constant flow of steam into the turbine, and that is done via some type of governor which compensates the speed to maintain its frequency. Okay, so now Now we have here a mechanical schematic provided from the webpage stated below. This schematic is a view of the feed water system inside of a boiler plant. Couple items of note on auxiliary items. We've talked about the turbine. In this schematic, the heat exchanger is the turbine. Let's start with the boiler. It is that octopus looking thing on the right, two balls, one on the top, one on the bottom, and then the lines between. The boiler is essentially an enclosure to provide heat to pressurized water. Most steam plants use what's called a water tube boiler. It has banks of tubes separated by heat insulation. The water is circulated through those tubes under high pressure and high temperature to get high pressure steam to blow across the turbines. How do we get heat into that? Well, there's three types of heat. We have radiation, convection, and conduction. Different uses, different fuels will use different versions of this, but let's talk about the definition of those types of heat. Radiation is the movement of heat from warm to cool. It doesn't use a medium. That is how heat passes through space. That's how the Earth is heated via the sun. Heat comes from the sun and radiates the planet. Conduction requires contact between a heat source and a heated area. Imagine a pot sitting on a gas stove. The burner itself, the flame, touches the bottom of the pot and it heats the pot. The pot then touches what's inside of the pot, and that heats the thing you're cooking. That's conduction. Convection, let's go back to the sun coming to Earth. Convection would be radiation heats the atmosphere. The atmosphere then keeps us warm via convection. Convection is the movement of heat via an intermediate substance, such as gas. In this example, the gas would be our atmosphere. Other auxiliary systems of note on this drawing, the economizer. On the left side of the boiler, there is that 4-columned looking Roman structure. That schematic is designed to talk about the economizer. It's a heat exchanger that sits within the flue of the combustion material that we're using to heat the boiler. We put it in the flue to preheat the water going into the boiler. It's a capability of improving efficiency. The flue gas is hot. It's almost as hot as inside of the firebox itself, and that heat is then secondarily used to preheat the water. That's a second chance on getting energy out of that combustion cycle. So like I said, it improves the efficiency of our overall system. On the right of the boiler, we have the condensate tank. The condensators cools the steam that is passed through the turbine so that it returns to liquid state and we can pump it back into the feed water system. In this drawing, the condensate goes into the deaerator. The deaerator also takes in clean feed water. But let's talk about the deaerator before we get to the clean pure water purifier section. The deaerator removes gases. It allows settling of the feed water. We don't want gas dissolved in our water into our boiler, into our turbine. It can cause corrosion in there. And speaking of corrosion, we need feed water purification. The entire left side of this drawing is basically showing that. We have the source. It could be groundwater, it could be the river, it could be a large lake. Whatever it is, we pump out of that, we go into a clarifier, let it settle, let the silt settle to the bottom, we draw off the top of the clarifier, run it through a filter. The filter then will determine what's going on with the water. Does it need to be conditioned? That's what the next tank is. You see the brine tank going into that. That's a water conditioner. Maybe a lot like what you have in your basement, a lot larger version, obviously. And it goes into a storage tank. It would have other chemical cleaning of what's needed of that water. We need the purest water we can get to go into our system. This water, feed water, is probably cleaner than anything you'd ever drink. The issue with dirty water is that it would bring in corrosion to all the small tubes in the boiler, corrosion to the turbine blades, and that causes mechanical failure and issues along the line. We need to reduce the amount of maintenance required. So that's what I have for this lecture. I thank you for listening. Please go back over, watch it again, view the slides, and go ahead and write down your questions, work through the problems designated in the book about this section, and come to class with questions for discussion. Thank you very much.